Much of the science research on the International Space Station is devoted to learning more about how the human body deals with being in the weightless environment for a long period of time, which will be the case during future missions to explore deep space. One way to determine how people respond to changes in their environment is to sequence their DNA and RNA. And now there is a portable tool designed for that task that is being tested on orbit. It's called the Biomolecule Sequencer, and this morning we're going to learn about that from the principal investigator, Dr. Aaron Burton of the NASA Johnson Space Center. Good morning, welcome, and thank you for joining us here at the International Space Station Flight Control Room. Dr. Aaron Burton, thank you for joining us.
Thanks for having me. It's a pleasure to be here.
Great. Well, let's first talk about the sequencing research. Can you explain to me just briefly how did you get interested in doing this research?
Yeah, well, in graduate school, I worked with functional RNA molecules, and we would look at the effects of mutations and how that changed the function of the molecule. And so we did a lot of sequencing from that perspective. And so this project is kind of building on that research, where we're looking at changes in DNA and RNA and how they might affect humans and biology in general.
Well, that's really interesting. So what's also fascinating is, from what I understand, this is the first time we've actually been able to do this in space, correct?
Yes.
And so can you just kind of run me through how is this research going to be valuable to us sequencing DNA and RNA in space?
Okay. So I like to think of DNA as sort of like a cookbook, and then the RNA would be the recipes in that cookbook.
Mm-hmm.
Genes will be recipes in that cookbook. And then if you want to keep your cookbook nice and clean, you would make like a photocopy of each recipe. And then if you wanted 5 people to be able to make your cheesecake, you would give 5 people those cheesecake recipes. And so that's kind of how RNA works, where RNA is the functional or the molecules that go on to become proteins. And so how an organism is responding to microgravity or another environment, you can tell from its RNA. So certain RNAs will be increased in production, and other RNAs will be decreased. And by looking at the changes in the levels of RNA, as the organism is responding to that environment, you can tell, oh, we want this pathway upregulated, we want this pathway downregulated. And then by looking at DNA sequencing, you can look for permanent changes. So this would be like mutations or things that are going to change a cell permanently.
Okay. And so what about, well, I guess, characterizing organisms that are in their environment and so in space, but how is this going to help benefit for deep space exploration?
So one of the limitations we have for exploration now is that we return the samples to Earth. And that's perfectly fine for ISS because it's pretty close. But as we move, and you want to send humans to Mars, for example, it's a 9-month journey, roughly. And so you're not going to be able to return samples every month to do that sort of thing. So we'd like to have the ability to do these processes in flight during the course of sequencing.
Sure.
Or exploration.
So I understand you brought some show and tell here. This is actually the device that we have now in space, correct?
So it's going to launch next spring.
Okay.
So we're working on getting it flight certified.
Okay.
Yeah, so this is the DNA sequencer.
And it's commercially available.
Yeah.
So can you run through what is the process of getting it certified for space, and what will the astronauts do with it?
Okay. So basically, this is the sequencer, and then this is a flow cell, and this is kind of where the magic happens. Mm-hmm. So basically, to get it certified for flight, the most important things are that we want to make sure that it's not going to hurt the crew or the ISS itself. And then we'd also like to make sure that it's going to work. And we can't really test how well it's going to work in microgravity because the ISS is the only place where you can get sustained microgravity for the hours that a sequencer would run. And so then once we actually get it in flight, there's on the flow cell here, we're going to send up samples that we've prepared on the ground, and the crew is going to thaw them out and basically inject them into a little sample port, close it, and then they push go, and then the molecules flow down into this. There's a little chip here that has nanopores, mm-hmm. And as the DNA or RNA passes through the nanopore, you get change in current that's diagnostic of the sequence, and so you can, from those changes in current, get back what the sequence of the DNA was. And so for the first flight, it's just a tech demonstration, basically. Do all the fluidics work? Can the crew members load the sample in space? Um, that sort of thing. What challenges are there? How well does the device perform? And then in the future, we'd like to build to where we're actually doing the sample preparation in flight.
Yeah, because
So,
we haven't done this before, so we need to make sure we know that it's actually working properly in microgravity, if there would be any changes or anything like that to that device.
yeah,
And so what do the astronauts do? They will be loading the samples into the device as well
yeah,
when they're in space, when they're doing
yeah,
this. Okay, and I understand you're also performing some testing here on Earth. Can you
yeah,
tell me about that?
yeah. So we're basically to try and eliminate as many variables as we can. We're going to prepare identical samples that they have in flight. We'll have them on the ground, and as close as we can to when the astronaut is actually doing the experiment, we're going to try to sequence the same sample on Earth, so that we'll know basically how well the sample is performing. So that basically, hopefully, the only variable will be the actual microgravity environment, rather than well, if it's a different sample or some process is different, it's sat around for a longer period of time.
Sure. Great. Well, thank you so much for coming out today and talking about this. When
Okay.
does this launch again?
Set in springtime of next year,
Okay. Well,
sometime
we
in the
look
March to
forward
May.
to hearing all about that and good luck on the continuation of your research. This is Mission Control Houston.